variant where you don't necessarily say here is all the information, send it. You provide information right in the beginning so that the MPI underlying MPI can start to set up its local tables and all that for it, start to make connections. And it's later on that, and it's similar to the non-blocking send, where you wanted to say, here is the data I want to send, give me the handle, the identifier in the request variable, and I'm going to come back later and check whether that request is complete or not. Here, I'm saying, here is the piece of, here are the parameters that I need to send. Here is the buffer, here are the tags and the destinations, but don't send it just yet. Give me a request handle which identifies this send request, and sometime later I'll come back and say, now you're ready to send it. MPI send start. Okay, this is initially this is essentially to get MPI started on the business of sending early, before you have the data ready. Right? If you do MPI send, you have to make sure that buffer is complete with the data you wanted to send. In this case, it doesn't have to be. All you need to know is where you are sending it, what is the tag, enough to get MPI's sending process to begin. And at later stage, you can say start when you have filled the buffer, so that at this point, all the MPI's process has to do mostly is just start to send that data. Okay.
Just the advantage which we have.
It's essentially pipelining, right? It's saying that you get started with setting things up early, and
setting things. So it takes. I mean, there's some computations and all is required.
It's not that much computation, right? It is more getting connections, making sure that a socket is available, or rather a port is available, and things of that sort.
So copying into buffer?
That's not always done, but yes, copying into buffer.
Copying buffer only data, right? This is starting.
Sorry?
Here we don't specify the
We
don't specify the data.
You specify the buffer here, send init has the buffer. So the pointer is known. Later on, you only need to say, I have told you about this request. Now you can begin.
So, does it not use persistent connections? It initiates a connection for each send and each receive?
No, it does use persistent connections.
That overhead is also.
It's reduced, right? But you don't know whether there is no guarantee that that connection has been persistent since your last send. Okay. It may also be that this is the first time you're sending to that particular machine. So there is persistent connection, but that all is hidden. A typical implementation will not keep it persistent for too long, because maintaining each connection requires some resources. So there will be some small number of connections it can keep persistent, and if you ask for more, then it's going to have to recycle some of that. There is a SendReceive variant. This is the last variant of point-to-point communication we're going to talk about, which basically says, send this piece of data and receive a response back. Okay, so it's essentially the same thing as calling a send followed by a receive in one function call. Okay, again, minor overhead removed. In this case, you have to send or provide the address to the data you're sending, as well as the address to the data where you will be receiving. Okay. Again, complete send tag is different, receive tag can be different. The source from where you may be receiving can be different from the destination you are sending. the type of data, the count of data. Of course, count you would make sense to always generally be different. It's probably response of something, but it allows, it's basically combining two function calls into one.
The difference is it is on two threads.
No.
Work there doesn't mean it is starting two threads each for sending.
What fork?
Semantics.
Oh, semantics. So it's not actually physically doing a fork. Okay, it is, the semantics says fork and join because you may be sending to someone and receiving from someone else. If this send has to physically happen first, and that receiver is ready to, or the receive is ready to match with some other send that has already happened, then it must wait for the send to happen. Right? So it's like these two send and receive calls are happening concurrently. So it is possible.
Write it as MPI send and MPI receive
Then the receive, unless you are doing asynchronous, non-blocking, the receive will have to start only when send finishes. In this case, that's not required, even if it is blocking. Both will block independently. Okay. All right. And the non-blocking variant, as it says, has a slightly different name, but the same parameters. So basically, everything we have talked about is point to point, right? One source sending to one destination at a time. It remains point to point, even when you want to receive from potentially multiple sources. You'll be receiving from one of them only. Right? It's like select on sockets. You can receive from any source by saying in the value of the recipient, from value of the source, MPI source any source. The buffer must contain enough space. The parameter, and as I had earlier mentioned also, the tag can also be any tag. So you don't have to say, I will only receive right now messages of type 369. You can say, send me any message, send it from any source, and I'm going to be ready to receive it. There are these standard types that you can send, the standard C types essentially. You can also create your own types, okay? So that you don't have to bother filling your structs on the other side. You can say, here is a struct, send 1 copy or 100 copy of the structs to the destination. Okay, so that detail can be taken care of by the underlying system. NDNS difference, whatever, the architecture difference, and it's an int here, then it's an int there. Okay. So these are the standard, and the ones that you generate are called derived data types. And I'm not going to go through the details of all of it, but essentially, in the beginning, for every struct that you may want to send, you create a data type, give it a name, provide how it is arranged, that struct, and later on simply call that derived data type name in your send function calls. Okay. This is not the only way to do it, but here is one example where there is an MPI defined data type, and you declare some type, some variable which is of that type, and you set that variable in variety of different ways. One is you simply call, so this is contiguous. The method makes an array type for an already pre-known type, a type that either is standard or something you have built before. Okay, so you can say that this type is an 10 integer element, an array of 10 integers or array of 10 structs or whatever. There are other variants. Again, as I said, you should go look up the details of it. You don't need to talk about all of these details in the class. You can make a vector, and in fact, you can get quite creative with how your structs are locally arranged and what it looks like to an MPI. You can create types by saying, here's a struct, and I am saying command a bunch of things that I don't really care to send, some other command, bunch of other things I don't really care to send. You can create a type by only sending these command fields. Okay, and that is being done in this vector and half vector variants, where you say jump so much and then pick out one more piece of data, jump so much, pick out one more piece of data of a known type. We can also create blocks of such strided memory fields. There is also type struct. So you can create a struct by giving it some of the details about the struct. And this will, you can of course look at more details on MPI manuals also, but all of this will be on the slides, so you can take a quick look just to see how to get these things started. There are other variants, and let me just skip through all of this. Yeah, I'll point out this thing. For most types, you need to commit that type. It's not just enough to create it. You commit the type before you start using it in subsequent send and receive calls. And this is something that's a common
Commit will be a runtime
problem. Commit is a runtime. Everything is a runtime.
call. So, I mean, how would the compiler compile the code if it does not know what a type is?
It's not actually compiling the code, right? You are basically storing some values inside the type, which says that when I am going to send 60 things of this type, how do you interpret the memory? Right? So that information is stored in this type variable that you are creating. Right? This, if you go back to this original example, you create MPI data type new type, which is a struct. Internally, it's going to store lots of information. And as you may define this struct, all that information is being stored in there. So it's not compiler generated. Right? So you have said this struct means first 4 bytes followed by the 16th to 20th byte and all that stuff. So all of that goes into this type definition variable. And later on, when you call send with it, MPI routine will interpret it and pack the data out of your buffer.
Yes, what is commit?
I don't really know what commit is doing. You probably need to tell MPI that this type is not going to change anymore or something of that sort. I'm not totally certain. In fact, MPI commit, I don't believe is part of standard either. It's an open MPI thing, if I'm not mistaken. Okay. Here's an example of how to generate something. There are variants where you explicitly call pack and unpack. This is also true of the or most of communication routines, including PVM that I had mentioned earlier, where you explicitly provide pack and unpack routines, which says here is some list of variables, you pack them into a string of bytes, you send that string of bytes, and on the other side you unpack it. Okay, and then original versions of MPI standard use the packing and packing style, and so they still continue to be there. And it's a little more generic, right? There's no understanding that there will be some stride, that there's some even steps you'll jump to figure out which data to send. So Pack can be a bit more generic. And so there's also an unpack version for it, but it's basically saying here is a data pointer, here is how many elements I want to send, here is the type that it contains, and create this pack buffer. Okay. Okay, I'm not going to go through the packing example also. It's rather simple and not important. So now we get to non-point-to-point communication. The examples are listed here. Some of them will make sense to you by just their names. Some of them will make sense to you very soon because you'll be doing a lot of that. MPI barrier will do what? Everybody in the group must get there. Okay? Which means everybody must call this function. And when everybody has called this function, you can proceed. MPI broadcast is one, sending to everybody in the group. MPI scatter. Does everybody know what scatter and gather operations are? Well, some of you know. What's scatter?
It's an array, for example, of 1, 2, 3, 4. So one goes to one computer, two.
Right. So it is a richer version of broadcast in some ways. Okay. Instead of saying here is a piece of data and send it to everybody, it says here is an array of data. Send the first to the first guy, second to the second guy, third to the third guy, fourth to the fourth guy. So it's not broadcasting the same element, but in some sense it's broadcasting an array, but it's not sending the array to everybody. It's sending one section of the array to one person. You can use it in many ways. In fact, you'll see, you'll use it.
It's like if packing together so many point-to-point together.
Sorry?
Packing together a lot of point-to-point, running group kind of. You're giving, you say, one-to-one like.
Right. So instead of sending one-to-one to everybody, you're basically saying in one primitive, send. So now there's no sequence involved, right? You're in pair. It's like fork, send, join.
So do you know the set of people who have the order of the receivers?
Typically, it's the entire communicator. There is no order of recipients.
Because you know one is going to one person, so that one is no rank.
No, there is no rank. You know that one is going to a specific person and two is going to a specific person, but there is no order in which they have to receive it. Right? So you don't have to say send to one before you send to two.
But the matching of data is.
Matching of data is from the index. Right? Your index and rank are going to get matched, but there is no notion that one has to receive, and only once you have figured out that one has received can you send to two. Okay, so there is no sequence among the sends. So it's like fork, send to all, and then join again.
What is the blocking policy in this? And then each of them receives the only.
I'll ask you that question very soon. Let me explain all these different versions of it, or different primitives, so to speak.
So the number of indexes in the array should be equal to number of different computers.
Yeah.
Or it divides the team.
It divides it equally. Those are some of the details which we will talk about, but there's a more higher level question to be asked. Gather is the inverse of scatter. Right? So you're saying you produce something, you produce something, you produce something, you produce something. Instead of me receiving from you, then you, then you, then you, I'll say gather everybody's result. I'll provide one array. The first person's result will appear in the first slot, second person's in the second slot, last person's in the last slot. Okay?
Isn't that a very dangerous operation? one of them stuck, you are stuck.
Which would be true even if you did it otherwise.
No, but in the other case, you can see, okay, this particular machine is stuck, and then do something about that.
Which you can do even now. Right? You can say gather, non-blocking gather, and then keep waiting, and you say at some point I'll decide that that machine is stuck. Right? So all of that will apply. It's just combining the primitive into one call. There is MPI all gather, which is gathering multiple things. So it's a variant of gather. So we will talk about it, but it doesn't have to be detailed out yet. MPI all to all is sending a whole bunch of things to everybody by everybody. So it's essentially lots of scatter and gather happening together. MPI reduce, you should know. What will reduce do? Open MP reduce, right? So you've got every location has some piece of data, and you're going to combine them using some associative commutative operator.
So it's basically gather plus doing some operation on that.
You can think of it that way.
And can you do operations with gather also?
No, gather you simply put it in the memory, right? And all reduce again is just like all versions of everything else, is a version of reduce where typically you reduce and get one result, give it to say node 0. In all reduce, result is going to everybody. Everybody is getting reduced. A reduced result. MPI reduce scatter is reduce and then scatter. MPI scan is another thing that you'll do a lot of. What is a scan? It is a prefix sum. What is a prefix sum?
Sum the prefix.
Right. So it's not necessarily just a sum, but sum operator, where in reduce you basically apply a reduction of the entire set and produce one result, which you can imagine is the result for the last person. If you apply the same operation on the first n-1 pieces of data, ignore the last piece of data, then you've generated a smaller reduce, right? A subset of the original reduce, and that becomes the result on the n-first. You can think of everybody reducing, but only reducing up to it, starting from 0. Okay.
Doing this scan in parallel automatically decides upon the division of the array whatever we are scanning based upon the number of nodes available.
Here, yeah, there's no guarantee that it will be done in parallel,
Okay.
just like for OpenMPI, OpenMP. Scan can be done in parallel. Sounds like, what is it? Everybody, so let's take prefix sum, where you're adding everything up to u, right? So everybody's result is the result of the previous guy plus one more thing.
No. If it is commutative,
Let's assume it is, so we are adding. The first one adds itself, does nothing. Second one takes the previous guy's result, adds to it its own value. The third one takes the previous guy's result, adds to its own value.
Do it this way, then it is not parallel.
That's the effect we want. But there are other ways to do it. Okay, so, sorry?
Everybody can simply broadcast its value and then everybody can receive
But then cannot get 3 numbers at a second. You can always do it in 2 steps.
Okay, we'll come back to it. We'll come back to it, right? So we've talked reduce and yeah. You can be reducing many things.
Can you explain how do you call a reduce connection?
That's the question I was going to ask you. Let's do barrier first. How do you do a barrier? Very easy, right? Everybody has to call it. Okay, I've got a few slides explaining. I'll go through them very quickly. The other parts I've already told you, but broadcast does what? It's something. So what you see in this table here is every processor has a row, and processors or threads go from the top row to the bottom, and every processor may have an array of data. Right? So processor 0's array is at the top row, and 1's array is at the next row, and so on. So broadcast basically says got one piece of data, and that piece of data has to go to everybody, every processor. Scatter says I have an array of data, right? So processor 0 has the array, and that array gets distributed among all the processes. Okay, so that's scatter, and the reverse is gather. Everybody has one piece of data, and it's all going to get collected into one array for processor 0. Here is the all gather version, where you've got everybody. In a gather, you are taking everybody's piece of data and putting it in processor 0's array. But in all gather, everybody is gathering it. Processor 0 is getting the gathered result, processor 1 is getting the gathered result, and so on.
How do you call it?
Same question, same answer.
Can you explain this?
The all gather? It's basically everybody, what happens in gather? One processor is taking everybody's result and putting it in one array, right? All gather, it's like whatever that processor was getting is not divided. Everybody is gathering. Everybody is gathering from the one element that everybody had. So at the end of all gather, it's not only processor 0 just that has the gathered result, but everybody. That's the only difference. Everybody is gathering. And all to all is taking it to the other dimension also.
But an all gather will require an all scatter happening.
Why? Everybody has a piece of data. Okay. So all of you have something, and I say gather. Okay. So gather means you give it to me, and I'm going to get a collection. So everybody has the assignment, and you give it to me. I've got a list of assignments.
But for that to do, I have to scatter it.
No scattering. Right? Gather means I'll take everybody's piece of data and gather it into one pile.
I was thinking it's like send receive pair, like scatter gather, it's a pair.
It's not a pair. There is one unique fellow who is going to gather it. Okay? And everybody's assignment gets collected into a pile at one place. In all gather, basically you're making a copy of this pile and having it at every place. That's the only thing. Okay?
So it's like everybody calling gather.
We'll talk about that shortly. We have to first figure out how to call gather in the first place. So only then it will make sense in the all gathers context. It's not even clear how gather happens. And so if you think about how gather happens, you can think about how all gather happens also.
All to all, it's a complete here, because in all to all, then every process should now have all the data. So
You already have.
So every process should have A0 to F0, then A1 to F1. All to all. All data goes to everyone.
All to all is essentially taking, it's not quite transparent. Is that what it is doing? Yeah.
It's not all to all, it's kind of, it's still selective.
So none of the process here is having all the references.
I need to check on this. It is all to all doesn't mean that all data has to go to all elements or all processors. Okay, all to all gather meant that everybody was gathering one element. Right now, everybody starts to gather different element. Okay, that's at least what is based on this slide. But I will verify that to make sure that that is the correct interpretation of all to all.
Like it was one dimensional and one gather, all gather is two dimensional, so all to all should be three dimensional.
Could be. I'm not sure. I'll take a look at that.
What it is doing probably is everyone is scattering all the data it has to go.
Yeah, which is the same thing what I said earlier. But it may be that it's not just scattering, but everybody's data is going to everybody. It's like all broadcast, which I don't think it is, but I will check on that. Should be what?
A0.
A0?
A0 this whole matrix. This whole matrix is only A0 copy.
Only A0 should go to everybody.
I think the right hand side is only a copy of P0. The 0.
Probably this is the copy which everyone has. Everyone it is three-dimensional.
No, it's not just a copy of A0. Not a copy of P0.
This copy is available to every processor.
This table is no. No. This table is the same table as before, meaning that each row corresponds to a processor, and that processor has the elements in that row to begin with. Okay, so this is saying that processor 0 had elements A0, A1, A2, A3, A4, and A5, which got scattered to everybody. Okay, but B's or processor, the second processor's elements also got scattered to everybody. Okay, so how would broadcast work? So we'll talk about the function calls now.
Is it broadcast only the hosts which are there running the MPI, or is it a kind of network broadcast?
No, it's not a network broadcast. It's broadcast into a communicator. So broadcast will definitely take communicator as a parameter.
But in case the network broadcast, the hosts which are there in the network broadcast, all of them are in the hosts list. Then
no. So it doesn't have to do network broadcast. In fact, it wouldn't be implemented as a network broadcast.
it would just do for all the ranks available in the communicator, just send it.
It would send on each LAN.
So, but then, if I am sending a network broadcast, that means I am sending one package. But if I am sending a broadcast in this communicator, then if there are n hosts, I will be sending n packets, right?
No, it may be checking, right? If there are multiple hosts on the same LAN, it can optimize. Standard doesn't say anything about it. It is definitely not blindly doing IP broadcast.
You also need TCP, right? It has to be. I mean, it has to be reliable. Even if you broadcast.
If it relies, all the implementations do rely on reliable communication, but that's not the standard's business. Right? Standard says MPI is going to provide you reliable communication. If TCP/IP doesn't, MPI has to implement it. Okay, so somehow it's going to provide to you as an application.
Isn't it a multicast?
What's a multicast?
So that you send to a group of IPs.
Multicast is not well supported. It's typically not available on most installations. Okay. Okay, so let's get to the business of figuring out how this may happen as a function call. How do you call the broadcast function such that one fellow is going to send, everybody is going to receive?
Rank is some rank group input to the rank.
Does this in parallel rank 0 to 10?
So would it work if you said one fellow says broadcast instead of send? You're basically replacing a send with a broadcast and everybody else doing receive.
Broadcast is simply broadcast. I think you don't want everybody to, you may not want everybody to receive.
Here actually you do. That's, yeah. The standard says broadcast means everybody has to receive. Because it's also a synchronization.
So if
Not as strict as barrier, but there is a loose synchronization associated with
one of the hosts does not receive this broadcast, then you broadcast again or some,
Right.
or you send that to that particular host again.
Right.
It's a loop of send.
Sorry?
Loop of send based on the variable.
So if it is a receive, then you have to send to everybody. Right? Which means you basically want a fork and a send in each of the forks, with the fork knowing which one it is trying to send to, and then a receive. Right? Which isn't the most efficient way of doing it, because then there are all these independent copies doing their own setups, own copies into buffers.
Share the buffer, right?
Sorry?
You may want to share the buffer.
You may want to share. In fact, you would want to share the buffers. That's why the broadcast function is there.
Fork every time. There can be a process for all 10 nodes that you communicate. You give it to that particular person. Rather than forking every time.
Right, but somehow you need to need all these sends to happen in parallel. Right? You don't want it to be sequentialized.
So if you have n processors and you have n nodes for the computing, and you have 10 processes on each node for communication.
That's a lot, potentially. And so that's why it's important to implement it as a primitive together. And one efficient way of doing it is for everybody to call broadcast. Instead of calling, you might have thought of it as broadcast send and broadcast receive, but there is no reason to separate that out. Everybody calls a broadcast. And in the broadcast, so if we look at, let's go through this slide first. Broadcast means it's going to be sent to everybody in your communicator by one of the people that is a part of this communicator. And it is not exactly the same as MPI barrier, okay? Typically, there would be synchronization involved, but it's not guaranteed that we've returned from broadcast that everybody has received it already. Okay? So if you have returned from, so in barrier what happens? Everybody calls barrier and you have received it if you have returned from barrier. You can be sure that everybody has called barrier if you have returned from the barrier. Here, that guarantee is not provided. Okay? It's not necessary if you have returned from broadcast that everybody has called the broadcast function. And so the broadcast function takes parameters, the message, of course, you need to send something. You need to send so many copies of some type. If to send broadcast is in reference to a communicator, you may be part of many communicators, so you have to specify that, just like all the other point-to-point functions. There is also one more function which says who is going to be broadcasting. Okay. So internally you know who is the broadcaster. Everybody must agree that he is the broadcaster. If everybody calls this broadcast method with that variable equal to 3, then 3's data gets sent, everybody else's buffer gets filled. And everybody is sending a pointer. And everybody is saying 5 ints. Right? One of them is filled. Others will get filled as a result of this operation.
How will that common value be arrived at?
How we figure out whether everyone is agreeing to the same value?
It's part of the program, right? You should know who we are receiving broadcast from whom.
How does it check? If different users have different values.
Then they don't match with each other.
We need to use first variant so that first broadcast gets over, then again broadcast.
Then there may be a voting process, right? You figure out who is going to be broadcasting. And then we are going to receive from that recipient.
But to come to a consensus,
If you didn't have this, right? Let's look at alternatives. In fact, I think let me close this. We'll continue the discussion because we're going to run way over time on the cassette. We'll do a short discussion now, but we'll continue it in next class also. We were talking about broadcasts, and I asked you to go think about all the different ways you might do broadcast and then gather and the other group communication primitives. Okay, broadcasts. This is what we had already looked at. Why? And if you just to remind you, broadcast is something that everybody has to do, meaning that recipient and the sender has to call, and they have to be consistent with respect to each other. Right? So, for example, message is a pointer to some buffer. The sender has this data when you call it at the sender. The recipients need to allocate this space, but can have whatever they like in it. It will get overwritten. And they all need to agree on the amount of data being broadcast. Right? You see here, there is no getting the request back, right? There is no getting the status back. Which means you cannot tell how many elements actually came, like you do in send and receive. Which means you better know how many elements came. Everybody has to agree on who's broadcasting, that route, and then this is in the context of a communicator. Right? So we've already talked about the fact that groups are associated with communicators, and communicators, so far the business of communicator was just to give you a local rank. So in your group you said you got 1, you got 2, you got 3, and there was no real need for communicator except to say, I am sending to 2. You didn't necessarily have to think in terms of communicate. But now communicator becomes important because it's a group communication. So whoever is on that communicator has to participate in this group communication. Okay, there's a question.
yes, why is there a need to have the size to be fixed? Or why is it not also
Let's discuss those things. It's not necessary that everybody expects the same count of same type. Okay, but what is expected that everybody reads the entire message. Right. So the count times the size of the data type has to be known. Okay, and this is more of a design decision more than any logical reason for it, because anytime you allow partial returns to happen, you've got to have a way to query was returned, right? And by design, all returned values are either success or failure, right? Nothing about the data, which means you need to have an additional way to query something. So all the receives had this status that you could get information in. This one doesn't. It could have had that. The reason it doesn't is not very strictly defined, not very clear. At the same time, broadcast is a bit more synchronous. It's not perfectly synchronous, but a bit more synchronous than sends and receives, meaning that you are expecting all the broadcasts to be similar in nature. They need to understand that we are on this primitive, okay? So that's the rough reason, let's say, for why a status flag is not added. Okay, there are other things not here, which you would have expected from send and receive. Tag is not here. Basically the same reason, right? We are not really expecting for lots of these broadcasts to be in flight. Right? This is not a non-blocking call. You can't say broadcast, 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 and later check if your broadcast happened or not. And so because these are relatively synchronous, you really don't need to say, I've got these many in flight and I need to figure out which of those messages I'm reading at the moment. Okay, so tag is also not provided, again, for essentially the same reason, very similar reason. What prevents you from non-blocking?
So right now,
Is it a bit more complicated to implement? Sorry, question.
it's non-blocking, right? Right now, I mean,
It is blocking.
default.
Blocking. It is not synchronous, meaning perfectly synchronous, like barrier, right? So you're not guaranteed that that fellow has already called the broadcast. But there's enough guarantee that when I have returned from broadcast, it has been matched. There are things that have been sent or sent from my buffer. They'll be there somewhere in the system. So it is blocking.
Blocking for receiving the data, not blocking for synchronization.
Blocking for send also. Blocking for everybody. Everybody.
No, what will be blocking?
What do you mean now? When we send, then we are expecting a reply from the other side, and then the block will be.
No. That would be a barrier.
So
Right.
what do we mean by blocking here?
Blocking means that
If I am a sender,
I will know that this will happen. Right? I can go ahead and change my buffer, message buffer. Either typically it is synchronous. So for example, OpenMPI implements it in synchronous way. But it doesn't have to be synchronous, implemented in a synchronous way. It can copy this message somewhere else, copy all the information you are sending, set things up, and return. Right? So it,
Before broadcast return, so any read or receiver sent before it are finished.
say that again.
Before I return from broadcast, any send or receive that I made earlier would have finished.
That's not necessarily true. There is guarantee in the standard that broadcast messages do not get confused with send messages, meaning that when I am broadcasting something and somebody is receiving something, this broadcast message is not going to get matched with a receive call. It's only going to get matched with a broadcast call. And the other thing is that messages remain in order. What I send first to a given recipient will reach there first. Beyond that, there's no other guarantee.
But are the broadcast messages ordered with respect to the rest of the messages? No.
Between a pair.
Between a pair, yes.
Yeah. Right. And typically broadcast messages may be implemented as loop and send. Because in the standard there is no guarantee for what kind of implementation one might choose. And that is done in some implementations. But the idea is that you can have more efficient broadcast. So for example, if you have a largish size of the group, then you can have some kind of log tree-based broadcast. So you send to a few people, they send to a few more, they send to a few more. So you can get there much faster.
Sir, we studied about probe. So that checks only the head of the buffer or the entire buffer for the tag. So I'm probing for a tag, particular tag. So just check the first message or the entire buffer.
Just so the tag comes early, so it doesn't have to check for the entire message. If you just want to know whether your message is being received or not, then it's enough to say that this is the recipient you had said, or if you had a wildcard, then you don't match it. This is the tag you had set, and if you had a wildcard, then you don't match it, right? But when you are testing whether a message has been received, then the entire message has to be there.
What I'm asking is, when I probe for a particular tag, for example, there are two tags 0 and 1, and so when I'm asking whether message 0 is there in my buffer or not, so it only checks the first message, the tag of the first message, or the entire buffer. Does it check the
No, for that there is test, right? MPI tests whether your request is completed or not. Probe is not for completion. Probe is like an early look, and so you don't have to look.
There are multiple messages in the buffer which are partially available, and I can look up for a tag of any of them. So I think what you want to ask is whether probe will look up for all messages in the buffer or only first message.
No. So that is one way in which it might be implemented, right? There is no need for there to be a buffer where all the messages are buffered. For example, you have said receive, you have provided a buffer. The MPI could directly put it in your buffer. Right? So there is no ordering among buffers, at least from the standards point of view. So there is no first message in the buffer. Okay. There's also a question about what if I want to broadcast and not everybody wants to read. Right? I just say broadcast and whoever wants to read. Why is that not easy to implement?
Because there will be no matching.
Why is there a need for a matching call? So one question is, how does the system know whether you are going to read or not? Right? Does the system infinitely keep all broadcast messages until everybody has read it? Right? There's no way to know. So then you will say, I'm subscribing to this message. And that means if people are not subscribed to it, then don't give it to them. Right? Which is essentially the same thing as subscribe and read versus just read. What about blocking versus non-blocking?
Saying that at least in the blocking version that should be
Should be what?
that unless all the processors read, it should not call that broadcast as
No. So question is, what would be required if you had to provide a support for non-blocking broadcast? Assuming that everybody is expecting to read it. For every broadcast I do, everybody in the group is supposed to read it.
There is no tag, so
Tag is one issue, right? Now those two are kind of dependent on each other. You add tag, right?
the rank of the recipient is.
Rank of the recipient is not there, meaning?
So how would you ensure that it's non-blocking? So if
How do you ensure is non-blocking is that you immediately return, right? Meaning that when you say broadcast, it takes down the instructions that there is a broadcast on this communicator, right? And it returns. And then you have to come back and query whether that broadcast has succeeded or not, right? So a request will be returned to you, just like non-blocking reads, sends and receives.
So we'll need to buffer somehow broadcast messages separately to make it? Because somehow let's say I'm a receiver of the broadcast message, then I haven't yet reached the broadcast instruction yet. So, but the message has received. So there should be some buffering that stores the message till I reach there.
Which is going to happen with sends and receives also.
Right. So that should be extended here, which is not right. Should not be there currently. Right.
It's not there currently. Right. So that would be needed. Why is it not? Why is it any harder than just sends and receives?
It may be harder because we need to buffer it for infinitely. Say, as the person said, that I'm a receiver and I may need to go to that buffer for a long time. So, system may not be ensured that whether everyone has done the same thing. So, till what period that buffer should be filled with those messages only.
So there is increased buffering requirement. Receive messages also require the same thing, right? When you're sending to somebody and that somebody hasn't come to the receive call yet, right? There is some buffering that's going to have to be provided. But now everybody has to come to this receive call, right? So meaning now everybody has to come to a broadcast call, and just this you still want to maintain that group communication doesn't get confused with point-to-point communication. So broadcasts, you do a bunch of broadcasts which are in the flight, and corresponding broadcasts need to get matched. Right? In send and receive, your send could match with the first receive it saw, right, from whoever, and receive would match with the first send it saw from whoever. But now everybody's broadcast must match to be kept in order. So I make 3 broadcast calls, somebody else makes 3 broadcast calls, which gets matched with which? It requires a bit of synchronization. Right? What if you have the same tag also? Tagging would help when you want to differentiate one type of broadcast from another type of broadcast. But you're just broadcasting a stream of messages of the same type.
But there's the same problem with like multiple sends. So if you have 3 sends to the same recipient with the same tag, then you have the same problem.
You do have the same problem, but it's a point-to-point problem, right? You are going to, so as far as this, so that's a programmer's problem at that point. Programmer has to make sure that this, if I wanted this send to match to this receive, I somehow ensure it. System is going to be able to match some send to some receive. System's problem is easier. But if you do it for broadcast, system's problem becomes harder because everybody's broadcast must be matched.
There is added semantics.
There is added semantics for this.
But why can't we treat it like you have it for y to one-to-n loop, so like sending like a send request n times to like n different processes.
Right.
And it's effectively n point-to-point.
You can. However, so let's take another example. I allow multiple broadcasts to happen. In first broadcast, processor 0 was the root. Second broadcast, processor 1 was the root. Third broadcast, processor 2 was the root. Then you have to make sure that 0th root has to be called everywhere first, right? Otherwise, there's no matching. There's a deadlock. Once root has to be called everywhere then. So let's look at this example. Oh wait, it's non-blocking call. This is for synchronous. So this example doesn't quite answer that question. These are communicators. Com01 is a group for communicators 0 and 1. For thread numbers 0 and 1. A group contains those 2 threads. Com20 contains thread 20 and 0. You broadcast always within a communicator. Okay. But we'll come to this. This is a deadlock because of synchronization. But it also require, even if it were non-blocking, it would require a similar level of synchronization or reordering inside the system. Okay. So let's in fact see what's going to happen here. We are going to broadcast at two places, in two groups, in each of the threads. Thread 0 says broadcast on COM01, which is the first. I only see mouse in my. So the first broadcast of thread 0 is going to have to be matched with another broadcast with the same route in the same communicator, right? So that is going to get matched with this one. Okay.
What does communicator mean?
Sorry?
What does the communicator mean? Like the last parameter?
Communicator is essentially the group within which this communication happens. Right? So far we have been using world as a communicator. That says every thread that we have created becomes a member of that communicator. But you can create subgroups. So
This broadcast only happens to thread 1.
broadcast meaning message is sent only to thread 1 because thread 0 is already here. And in the meantime, thread 1 has not called this because it has earlier called another broadcast which gets matched with thread 2, right? That communicator on 1.2. But it can't get matched yet because thread 2 had earlier called another broadcast that got matched with thread 2.0 with communicator 2.0 on thread 0. But that can't get called yet because the first broadcast hasn't been matched yet, right? So if it is synchronous, meaning this cannot proceed.
So this blocking is, why does the sender block? Can you come to that again?
Sender blocks for many reasons, right? The only thing that as a user you are guaranteed is if a blocking call returns, then your call has been made.
Yeah. By that you mean your matched everywhere in the group?
It doesn't guarantee you anything. It doesn't guarantee you of anything of that sort.
So then I'm not able to understand why thread 0's first broadcast will wait. For what will it wait? We are saying it will wait for the matching part, right?
If it is synchronous.
Right, for synchronous case only. So how can it know that it has been matched in all the threads within its group? There are like numerous threads. There can be numerous threads. So it is as good as sync. Okay, you are saying it synchronous. Like a barrier.
Well, barrier is synchronous. You are not required to provide barrier facility in broadcast. That doesn't mean that the system will make sure that you don't synchronize. Okay, the system. It may not synchronize. So it becomes a double hard, kind of double jeopardy for the user because it can be as bad as synchronous. And on the other hand, when you rely on synchrony, it doesn't provide you.
When we are just taking the worst case of the human being.
Yes, right.
The standard but does not say specifically that this would happen.
No. It is possible for under certain circumstances. So it's not even true that it's always going to happen for a given implementation.
OpenMPI does this.
OpenMPI does this, but even if OpenMPI will return to you before actually synchronizing with the matching broadcast, it is not guaranteed that it will return to you in this case. right? Because there may be, if its buffer may be full, so it can't return to you until it has cleaned out your buffer. It can't clean out your buffer because it can't copy it into your buffer, and it can't copy into your buffer. It can't copy into its own buffer because it's waiting for some other thread to get matched and empty some space. Right? So just because it is able to return sometimes doesn't mean in this situation when you did this call, it was in a position to return. Okay.
What synchronization does it provide then? That it has been received on all the buffers you wanted to send it to? Though they may not.
There is no synchronization being provided by the standard.
You said there is weak synchronization. What weak synchronization?
Weak synchronization says that when all of them are going to make broadcast calls, right, and this is going to get matched with them, and so that is that level of synchronization, that it will get matched with all of them. You don't know when that is going to happen.
You're saying that if there are two threads, one does a broadcast, it can move ahead.
Yes.
When the other one does a broadcast, it will be matched to that particular broadcast. That's it.
Yes.
But then what? This is normal SendReceive semantics as well, right? I mean, without.
But SendReceive is point to point, right? Here you have said something about the entire group. So SendReceive is also weak synchronization.
You have not said anything significant.
So you think everything I should say should be significant?
No. I mean, I thought that there was something. The weak synchronization meant something.
I had said that earlier also. For send and receive. Here there is weak synchronization for the group. There it's between the points. Right?
Actually, you have created consist only 2 nodes. So
in this case, that doesn't have to be.
Send and receive.
Yes, in this case it is very much like send and receive.
So it ends up to become like any point to point. Like you mentioned this.
What becomes a? What becomes a?
Telling the group to take n0 to 1, 0 to 2, 0 to 3.
Yeah, effectively. Right, but that's not necessarily how if you implemented the broadcast using a bunch of receives, you would probably get a slightly different behavior from the implementation. Versus if you implemented broadcast as something that is more synchronized, which is what most implementations do. Meaning that when you've returned, the standard doesn't guarantee that anything has happened on the other end. But on most implementations, something would actually have happened at the other end. Okay, and in OpenMPI that is the case.
There's a parameter indicating the group com01. So how do we write the parameter for say 3 or 4 nodes?
No, you create a communicator.
The com word, we write com word, so that includes all the nodes.
Yeah, so that's a constant. It's like 0, right? So this is like file descriptor 0 already means something. So it's like that. A constant communicator which exists in OpenMPI is a pre-built communicator which automatically is filled in with the members that you create in the group. Any other communicator, you have to physically call functions to build. Okay. All right. So one final question about broadcast. Why is it that you have to say, I want only to receive broadcast from root number 0? Can you root number so and so? In send, in receive, you could have said any sender, any tag. Here you have to be very precise. And this is another reason why it's a little bit more synchronous than send and receive. But why couldn't we say?
Because everybody is calling broadcast, nobody is calling send or receive. So you need somebody to be chosen as a sender.
whose data everybody collects. So if you say any, then who's actually sending?
Okay. What if, why wouldn't I say, let's do not a broadcast, which is actually in asymmetric operation, right? One sends and some receive. So why shouldn't I just say bcast send, bcast receive? So bcast send would be automatically would mean send to everybody. Bcast receive will say receive bcast from anybody. Why do we need a new primitive or this group mechanism where the same function is called by everybody with some parameters meaning different things at different places? Okay, let me stop here. We'll take just a quick break and we'll continue the same question after the break.